International Faculty Development Program conducted by the Department of Artificial Intelligence and Data Science of Eastern Engineering College. The guest speaker for the day is Mr. Richard Rex. He holds a master's in computer science, machine learning from Georgia Institute of Technology. He is also the university honors student. He is currently pursuing his research in the Seismic Laboratory for Imaging and Modeling. Thank you so much for accepting our invitation, sir, and giving a lecture on Julia. The session is yours.
Thank you. I'm just going to share my screen. So if you guys could confirm that you can.
Welcome.
Morning, ma'am.
Have a great session.
Yes. Thank you. Can you see my screen?
It's not visible.
Can you guys see my screen?
Yes, it's visible now. Yes.
Okay. So hello, everyone. First I'd like to thank Ms. Kale Chelvi and all the organizers for giving me this opportunity to present to such a knowledgeable audience. I hope everyone learned something from today's session. So let's get started. So I'm going to be talking about the programming language Julia and its capabilities in the context of scientific computing and machine learning. Julia is basically a high-level, general-purpose, dynamic programming language whose features are extremely well-suited for numerical analysis and computational science, right? So my goal is not to make you an expert in Julia, but it's really just to give you enough exposure and reasons to start using Julia in your own research work going forward, okay? So let's get started. I ended up getting an awesome introduction, so I'm just going to skip the slide. However, my email is on the slide, so if anyone would like to reach out, have any questions or collaborate, please shoot me an email. I've split today's content into 4 wide topics. So I'll start with some basic syntax and then cover some capabilities of Julia, then talk about machine learning in Julia, and then do a live coding session where we'll build a neural network to do something based on the things that we'll cover. I'll also leave some time in the end for questions. So the first reasons that anyone picks up Julia is to help solve this trade-off that's age-old in programming, right? Which is fast coding versus fast execution. It's always been the case where you can only have one or the other, but Julia really helps solve this paradigm. So Julia, like Python, R, or MATLAB, it's nearly as fast as C, right? But it's also really expressive and it allows for fast interaction with Python. So it has its roots in the domain of scientific and HPC, but it's becoming more and more mature as a general purpose programming language. So starting with data types, Julia variable name can include like a subset of Unicode symbols. So for example, let's take a Greek letter, right? In most Julia development environments, including the console, to type the Greek letter, you can use like a LaTeX sort syntax, typing a backslash, and then you can type in alpha, which lets you use the Greek letter alpha. Using the same LaTeX syntax, you can add subscripts, superscripts, and so on. So their main types of scalars are, int64, float64, and characters, which are initialized on the slide. As you can see, x equals a, and we have string initialized, which is x equals abc, and we have booleans. Moving on to arrays. Arrays are n-dimensional mutable containers, right? So they're parameterized with the type of object that they hold and the number of dimensions. So as you can see, we have a equals array t comma 1, which is basically initializing an array of type t, which is a generic type here, and dimension 1. You can also initialize an array as a vector, which is basically a one-dimensional array. Or you can also do a equals brackets 1, 2, 3. And you can also notice that arrays don't have to be homogeneous. They can contain different types. So in the part where we have 10, comma string, comma boolean, these are all heterogeneous types, right? And they all work fine. So there are several ways to create arrays. And as any language, you have methods to sort of like add, delete, and manipulate the arrays. And a two-dimensional array is a special case, which is denoted as a matrix, right? And each element of either the vector or the matrix can be another vector or a scalar or another matrix, right? The main difference between a matrix and a two-dimensional array is that in a matrix, the number of elements on each row must be the same. And then you can use all of these linear algebra rules for them. You also have tuples at the very end. So let's move on. Looking at control flow, which is basically loops and if, else, do, and so on. They're supported, and parentheses around the conditions are not necessary, right? So multiple conditions can be specified in the for loop. And break and continue works just as similar to Python. So there are some examples of list support in Julia. So you can see we're calling my function for each of I in the array of 1, 2, and 3. And for the second one, what we're basically doing is getting the value from the dictionary after we enumerate the list. And enumerate returns an iterator to tuples with the index and the value of the elements in an array. And zip, in the third example, returns an iterator of tuples pairing two or multiple lists. Map finally applies a function to a list of arguments, right? And do blocks, what they do is they allow us to define anonymous functions that are passed as first argument to the outer functions. So if you can think of a lambda function, which is what the find all x maps to x equals value, and we pass in my array as a substitute for x, right? So this is a lambda function, and it expects, we can map this to a do function as well, which is takes in a function and then it applies it to all the other ones. So first time is an argument, and then it's a function which can be returned at posteriori with the do block. Right. Structures. So structures was previously actually known as types. It's now renamed as structures, but it's most other languages call it class, right? So it's basically structured data, and they define the kind of information that is embedded in the structure. So we have a set of fields, which might be called as properties in other language, and then we have individual instances, objects, and they can be produced each with its own specific values for the fields in the structure. So there are composite types in the sense they're not made of a fixed amount of bits, and instead they're made as primitive types. So you can imagine there's a bit of optimization in how these types are defined. So here's how you define a structure. Before that, it's important to know how you define the type. So we have A colon B means that A must be a type of B, and we have A less than colon B, which is basically A must be a subtype of B. So int64 would be a subtype of int, right? So things like that. So here's how you define a structure in Julia. We have mutable struct, we have my own type, and it's parameterized by a type T, which needs to be a subset of number, and it has three properties. So property 2 needs to be a string, and property 3 can be some sort of type. And you can actually omit the mutable keyboard in front of the struct, right? So you see mutable struct. So omitting that enforces that an object of a type has been created and its fields no longer can be changed. So that's what that's going to do. Structures are immutable by default, right? So mutable objects like arrays remain themselves mutable also in an immutable structure, which is important for manipulation. Although obviously less flexible, immutable structures are much faster. You can also create abstract types using the keyword abstract. Abstract types don't have any field, and objects cannot be instantiated from them, although concrete types can be defined as subtypes of them, right? So you can initialize a struct similar to other languages where you just call it as a function and then you can access the properties. So note in the example how we're passing in string as our second argument, right? Something. If we were to pass an integer, this would not work. And that's important to note because we've defined that property too as a type string. All right, so what we've covered so far lays the foundation to build this object-oriented design-based code in Julia, but there are three big elements that distinguish Julia from implementation of pure object-oriented paradigm, right? So firstly, you don't associate functions to a type. So you can never do, my object dot function and call it. Rather, what you have to do is pass the object as a parameter to the function. We also have that multiple inheritance is not supported. The third one we'll cover a bit later on. Okay, so functions. So functions can either be defined line or you can use the function keyword. So the first definition is f of xy is 2x plus y, which is basically an inline definition. And the second one is use the keyword function. And arguments are normally specified by position, while arguments given after a semicolon are instead specified by name. So we have my function a comma b equals 1, semicolon c equals 2. So c needs to be specified by name, right? So the call of the function must respect this distinction, and calling positional arguments by position and keyword arguments by name. So if you see the initialization where we have my function of 10 comma c is 13, what that's going to do is use the default value of b and then use 13 for c. Sorry, 3 for c. That is a typo. So functions can either be specified regarding on which types they work with using templates, right? So very last we see function where x needs to be of type t and y and z need to be of type t2, where t is a subset of number and t2 can be any type. And this is just resulting 5x plus 5y plus 5z. And this function defines two types, right? So which we just covered. So you can call this, you can initialize this with, or you can call this function with say like 1, 2, 3, which is fine, right? Or even like 1 comma 2.5 and 3.5. And that's because y and z are still the same type. They would be of type float. But you can't do 1 comma 2 comma 3.5 because y would then be of type integer and z would be of type float. So definition of my function constrains that the second and the third parameter must be the same type. So moving on to input and output. File reading is really similar to other languages where you just first open the file, specify the modality, which is either read, write, or append, or you can bind the file to an object and finally operate on this object and close it when you're done. So if you can see in the example, we write open this file with the write modality, and then you can write whatever you want in it. In this case, we're just writing test. Then we just close the file, right? So a better alternative is you can encapsulate this file operation in a do block. So that closes the file automatically when the block ends. So in the example where we have open file, where we do some sort of for operation and then we end this. So this actually closes the file at the end, right? So there are a lot of libraries that have been built to handle different types of data. For example, we have csv.julia, which is used for parsing like Excel sheets, and we have WebStream, which can process web pages, and we have something to process spreadsheets, and we also have HDF5. HDF5 is a general purpose library. It's a file format for storing scientific data, right? So it can store two types of primary objects, which is data sets and groups. I'm sure a lot of you might be familiar with that. So moving on to plotting. So plotting in Julia is pretty versatile, right? And it's a powerful feature that allows users to create like really high quality visualization for data analytics, research, and so on. Julia provides several packages for plotting. Each offers a very unique capability and style. So let's explore some popular plotting packages in Julia and showcase code examples to illustrate their usage, okay? So in Julia, there's something called plotting backend. It refers to the specific library or software that's responsible for generating the visualization, right? So this is going to take the plotting commands and the data that the user gives, and then it's going to act as an engine that handles the literal rendering and display of plots. So this may vary device to device, which is why it's important to sort of abstract this concept away. Plots is plots are Julia. That's what the example is based on. So it's this high-level plotting package. It provides like a unified interface to multiple backends, right? Including GR, PyPlot, Plotly, which we'll see in a bit. So it offers a very simple and intuitive syntax. So here's an example of creating a plot using plots. One interesting aspect is that you can really switch very easily between plotting backends, right? So plots, since it's sort of this high-level interface, you can write code in this consistent syntax without choosing the preferred backend for the actual plots, because you can distribute the code and people can set the backends whatever they want. So this means that with plots, you can write your plotting code once and easily switch between the backends without changing your code. So this flexibility is really desirable in a plotting functionality. As you can see, we have some nice plots with very little code, so it works pretty well. There's some other great packages as well. One of them is called Gadfly, which is a grammar of graphics-inspired plotting packages. It focuses on creating really customizable visualization. And there's also Plotly, which is an interface to the JavaScript library, but it enables like interactive and web-based plotting in Julia. You might be wondering, how can you use JavaScript? We'll get to that. It often covers like a wide range of interactive features, and it also has like complex visualization using like simulations as well. So it's pretty cool. So you can create 3D surfaces. You can also offer collaboration with other packages like Megalite, GR, and Make. And they all have their own strengths and styles. You really just have to go through them and pick whatever caters to your plotting needs. But there is a rich ecosystem for data visualization in Julia. So that being covered, let's jump into why you should even consider Julia. So far it seems like Julia is, this cool language, but why should I really switch from Python, or even C, whatever the use case is? We have a chart that shows execution time for different micro benchmarks across different languages. So these micro benchmarks, while they're not comprehensive, they do test compiler performance on a range of common code patterns like function calls, string parsing, sorting, recursion, array operations, and so on. The results depicted don't include compile time, but we can see that Julia performs on par, if not better, than a lot of the competitors such as MATLAB and Python. And obviously it does not perform as well as C, but there are several reasons for that, including the fact that Julia is dynamically typed. So as you can see, it works pretty well. It's pretty fast. And why exactly is that the case? So there are several reasons why Julia performs well. So understanding some of these could be helpful in determining if Julia is something that you can benefit from, right? So the first reason is Julia employs a sophisticated just-in-time compiler, which is also known as a JIT compilation system. So this dynamically compiles code during runtime. And this optimization offered by JIT allows for efficient execution of frequently executed code paths. So specialized code generation based on actual types can now be ensured that the generated machine code operates on these specific data types. So you eliminate all the performance overhead associated with dynamic typing. Now this allows for dynamic typing with optional type annotations, which means variables can hold values of different types, right? It also supports optional type annotations, allowing you to specify types if you need them. This combination of dynamic and static type helps in writing concise and efficient code. In summary, JIT takes the static and dynamic types. It takes all this language optimization and provides a very powerful mechanism for achieving high performance execution time, which is why you see these really low times on these charts. So Julia, unlike Python, is not interpreted, right? Which means it's a compiled language that is primarily written in its base. So it's an interesting fact. If you notice, if you take any sort of machine learning package like TensorFlow, less than, I think about like 70% is actually written in its base language, whereas Julia is 100% written in Julia. So that's a really cool thing. So Julia is compiled at runtime, whereas traditional languages are compiled before execution. So when you write really good code, Julia can be as fast and sometimes even faster than C. So it's a unique type language that has its quirks and features. That brings us to one of the coolest features in Julia, which is multiple dispatch. So multiple dispatch is a relatively simple concept. So functions can have multiple definitions as long as each definition restricts the types of argument differently. So this is perhaps one of the best features of Julia language. Some of you might draw comparisons to the method overloading in languages like Java, but it's important to note that overloading is static, right? It's not a replacement for dispatch, which is for dynamically typed languages. As a simple example of dispatch, let's consider the following code snippet on the screen. So we have three functions where we should learn their detail later, but basically the input to these methods have different types, right? So the notation X array string 1, which we covered in the basics of Julia, we see that this forces X to be an array of type string and one-dimensional, right? And the second one is pretty similar to that, which is it needs to be a one-dimensional array of integers. The third one, it needs to be a one-dimensional integer of Booleans. So if each of these definitions had an implementation, it would leave us with one single function, sort. And you could use that to sort strings, an array of strings, an array of integers, or an array of Booleans. It would treat each case differently. So what makes Julia's multiple dispatch unique, right? Every time you call a function in Julia, there's a method lookup, right? And that's from the perspective of the Julia developer, right? That's what happens. There's sort of method lookup, and then there's a type lookup, and then it executes that function. But code runs as if that happened every time, right? In other languages, you want to support multiple dispatch, that's not what happens. Only functions tagged in special ways use multiple dispatch. Otherwise, you have these regular function calls that are performed. And this makes sense, right? Why do other languages limit the use of multiple dispatch? Because until Julia came around, multiple dispatch was extremely slow. And that's not hard to imagine, right? Because you're doing a single dictionary lookup in constant time, and you potentially have to do a linear search for the types, right? To make sure which type in that function that you're supposed to be executing. And so functions can have huge method tables. So how does Julia solve this problem? Julia is designed around the idea that keeping types as stable as possible. So in a language like Python or JavaScript, that's not the case. Fields and methods can get added at runtime or removed at runtime, right? So the types of individual fields themselves can change. Julia types are much more locked down by design. So when you define a composite type, you fix the number of fields and their types. So code analysis done by the JIT compiler becomes much easier. The behavior of the code becomes far more predictable, which makes it possible to identify more cases where the method that should be located when a function becomes entirely deterministic and predictable. So in summary, it does everything dynamically, and it does this optimization that makes the JIT compiler take care of everything. So what is another use of this multiple dispatch? It's going to be code reusability. right? So one simple example of this flexibility is on the screen. It's the show function, which is defined in the Julia standard library. It's used by Julia to display a value in different contexts, right? So this context can be a REPL environment. A REPL is basically read, eval, print, loop. It's this command line tool. I'm sure a lot of you might have used it. It could be a notebook, or you could be any integrated development environment. So methods matching the following two signatures can be added to the show function, right? So we have show IO, which is of type IO, and we have MIME, and we have X. So the IO object represents a target for the display of value X. IO could be the console window, a file, a text string, a socket, or a graphical display. Value X could be any sort of simple number, date, text string, or more complex object, such as a dictionary or an array. Unlike these object-oriented programming languages, you can extend the display functionality among multiple dimensions, right? You could add show methods for entirely new IO subtypes. So let's say we created special types to represent the temperature units, Celsius, Fahrenheit, and Kelvin. Methods could be added to the show so you can represent these temperature with the right unit. So in the extension, what we see is show IO, type IO. T is of type Celsius. The second one, T is of type Fahrenheit, and T is of type Kelvin. So we added all of these extensions to the show function without having to modify the base library, right? So to understand why this is so powerful, allow me to point out some problems you would face trying to replicate the extension mechanism using, any sort of OOPS programming language. So you could design a system where every object had to implement a show method to be displayed, but that choice has issues, right? All classes would then have to inherit a base class which has the show method, and each object would get the same representation on every IO object. So that prevents you from distributing your code as a reusable library, right? So if you distribute a library, people should not have to modify the source code to extend it, right? So Julia managed to turn starts off as a performance disadvantage into being a performance advantage. So you see, because of this, Julia function calls will be generally significantly faster than single dispatch calls in object-oriented programming. When you have lightning fast multiple dispatch used everywhere, your coding style is going to start to change. So having this multiple dispatch has a really profound impact on software engineering practices in the Julia community. And this is what towers over Python, right? So this leads to like really fast and compact code that's easy to develop. Many languages have some form of dispatch, but the things that make multiple dispatch great in Julia, that it's used everywhere. And it's so fast that there's no performance penalty for using it. It might be worth to note that some confusion might be among you guys that, hey, there's type annotation in Python. Isn't that the same thing as this multiple dispatch? But that's not the case, right? Type annotation is purely for the user. The standard Python interpreter does not use type annotations. Moving on to metaprogramming. The strongest legacy of Lisp I'm sure if you might be familiar with it, but Lisp was this really powerful language developed by a lot of smart people. And so the strongest legacy of Lisp in Julia is the metaprogramming support. So like Lisp, Julia represents its own code as a data structure of the language itself. So and since code is represented by objects that can be created and manipulated from within the language, it's possible to program, transform, and generate its own code. So this allows for sophisticated code generation without extra build steps, and also allows true Lisp-like macros operating at the level of abstract syntax trees. So in contrast, preprocessor macro systems like C and C++, what they do is they perform textual manipulation and substitution before any actual parsing or interpretation occurs. Because all data types in code in Julia are represented by Julia data structures. That's not the case here. So we have really powerful reflection capabilities that you can look into, like the internals of programs. So let's take a look at the example starting with the left column. So every Julia program starts life as a string, right? So the next step is to parse this string, and we're going to parse it into an object, which is called an expression. And this is represented by a Julia type, which is called EXPR, as you can see at the very bottom left. So these objects contain three parts, right? So in the second column, we see these three attributes of the objects. So it's namely a symbol, which identifies the kind of expression. Symbol is in turn string identifier. So in this case, it's ex1.head, which is call. So that's our symbol. Secondly, the expression arguments, which may be symbols, other expressions or literal values, which we can see are an operand and two ones. Right. So finally, the expression result type, which may be annotated by user or inferred by the compiler, which is of type any. So you see ex1.typ, and that's the type of this program, which is of type any. And we see the arguments, which is 1, 1, and we have this operand, which is plus. So you can also define this expression using prefix notation, right? And that's the third column. So we see that these two expressions constructed here is ex2 is expression of call. And we're going to initialize it with operand plus and 1, 1. And what's interesting is ex1 will evaluate to ex2. So these two expressions are by direct construction equivalent, right? So the key point here is that Julia code is internally represented as a data structure that is accessible from the language itself. Right. Part 2 of metaprogramming. Macros provide a method to include generated code in the final body of the program. So the main benefit of using macros is faster execution time, right? So during pre-processing, a macro is expanded and it's replaced by its definition each time it's used. So a function definition occurs only once, regardless of how many times it's called. Macros may increase code size, but they don't have the overhead associated with function calls. Macro maps a tuple of arguments to a returned expression, and that expression is compiled directly rather than requiring a runtime evaluation call. So macro arguments may include expressions, literal values, and symbols. So here's a very simple macro, right, on the screen. We see that we have macro say hello, and it's just going to return this executable, which is print, and it just prints hello world. So macros have a dedicated character in Julia syntax. So if you see the @ sign, followed by the unique name declared in macro name. Right. So in this example compiler, what it's going to do is replace all of this @say hello with println hello world. And if you enter, @say hello in the REPL environment, the expression executes immediately, right? So here we see the example where we open the compiler and we say @say hello, and it just prints hello world. So this @say hello is a macro that's represented as a data structure in Julia. There's a lot of layers of complexity for macros and metaprogramming, but that is the summary, and this enables really advanced code generation techniques and DSL development. DSL stands for domain-specific language, which makes Julia highly extensible and adaptable. All right, so next cool feature about Julia is interoperability. So this is the ability of different systems, devices, applications, or products to connect and communicate in a very coordinated way without any effort from the end user. So in our context, it's to interact with other programs from other languages within Julia code. So Julia's interoperability with other programming language is a very powerful feature. So this enables communication between different ecosystems, right? Using this, developers can combine the strengths of multiple languages and utilize existing libraries and tools to enhance their Julia projects. So let's see how Julia uses interoperability for Python, R, and C++. Julia here provides a pretty straightforward and efficient way to call Python, right? So you use this package called PyCall, and you're going to import the library math, and you're just going to call math.sign mathpy, and this just prints the result of sign pi over 4 from Python, right? And similarly for rcall, you execute this piece of R code using the library rcall, and we have cxx for C++. So this interoperability with C++ and Python and R, you can directly use this within Julia. So you can, if some code is really fast in C++ and you need it to stay in C++, that's fine. You can just call it from C++ and use it in Julia. So what are some actual use cases of this? So you can continue using Python and R libraries, right? So there's Python, I believe, is about like 25-year-old ecosystem, and it really shows, right? Compared to Julia, it's very developed. There's a very wide range of Python libraries. So expanding the capabilities of Julia in your project, it might be inevitable to use some of these libraries. So you can leverage like popular even machine learning frameworks like scikit-learn or TensorFlow or Python within your Julia code base. And you can also optimize with C++. There are some things that just can't be written faster than C++, right? So for those things, you can leverage those C++ from Julia. And this is especially useful for numerical computations and scientific simulations, which I believe that C++ is still the leading language on. So, and also legacy code integration. So if you have a lot of legacy code, you can avoid the need for a full re-implementation, right? So this interoperability just lets you have the smooth transition and just reuse all your code. And there's also something called polyglot programming, which is combining like multiple languages to leverage their respective strengths and create like cross-language development. So that's an important use case for this. So an interesting fact is that Julia's interoperability is not limited to calling code from other languages. You can also allow other languages to call Julia code seamlessly. So this bidirectional interoperability really enables Julia to act as a powerful computational engine that can be utilized from different ecosystems, which is really cool, right? And you can also seamlessly pass data structures, arrays, complex objects between Julia and other languages. So you have the smooth integration and collaborative workflow. So it's also worthwhile to note that these mechanisms include automatic runtime type conversion, because you might be wondering that C++ is not dynamically typed, right? So how this works, so there's this automatic runtime type conversion, which converts all the types pretty transparently. That reduces the friction in passing data back and forth. So we've covered a couple of languages, but Julia Interop is this GitHub organization that decided to create packages that facilitate this cross-language development. So they have a lot of packages for any language you can think of. So if you have a specific use case, you just have to refer to Julia Interop to see whatever you can do. So for those not familiar with parallel processing, it is basically the ability to speed up computation by leveraging multiple machines. It really helps target larger problems, and it lets you perform research at scale. So the work at my lab actually involves this implementing like distributed neural architectures in Julia using a scalable abstraction, which is also written in Julia that we're working on. So the topic is really exciting for me, right? Parallel programming is what enables anything at scale, right? So in Julia, this enables like multiple CPUs, either single machine or across a different cluster to enhance whatever speed up that you need. Julia provides a multiprocessing environment based on message passing, where programs can learn multiple processes with separate memory domains. So let's just explore the key aspects of parallel programming, including best use case, implementation, and usage. But if you guys have studied anything like OpenMP or MPI, it's a lot easier compared to those. So its approach to programming, parallel programming, simplifies the code structure, right? It uses this high-level operation that resembles function calls rather than low-level message passing. Whereas if you take, a C and you'd use OpenMPI, it's this low-level message passing interface. So the implementation is built on two fundamental primitives. So we have a remote reference and remote calls. This remote reference allows any process to refer to an object stored on a specific process, and it provides access to shared data. On the other hand, a remote call is a request by one process to a function on specific arguments on another process, right? So this mechanism of communication and coordination abstracts away all the complexities of low-level message passing, right? So if you take, C++, what you have to do is you have to make sure your data is distributed properly. You have to take account of edge cases. You have to you have to allocate memory. You have to do all these little things that just almost wants you, makes you hate parallel programming. But a lot of use cases for this parallel programming in Julia, right? So you have parallelization of independent tasks like matrix operations, image processing or Monte Carlo simulations. All these things they're very embarrassingly parallel, right? So they're very easy to parallelize. And you can also target large-scale simulations. We know that parallel programming is very suited for running simulations across multiple parameters, which enables like fast exploration of simulation space, right? It's kind of like a GPU, but for simulation. So parallelization can be employed to expedite optimization algorithms. So you can search optimized solutions or parameterized configurations in parallel. Distributed data processing is also something that's a use case in Julia, where you can extend distributed computing for different data sets across multiple nodes in a cluster. So you have a huge data set that needs to be processed. You just split it up, and that's the end of it. Julia provides several mechanisms and packages for parallel programming, the most popular one being distributed standard library. So here's an example of using parallel programming in Julia, right? So in the code example, the @distributed macro distributes the loop iteration across available worker processes. So we first define this function, right? When we define this function, which takes an x and just returns some result, which could just be the identity function. So let's just say it returns x. And we're adding 4 additional workers here. So we're doing add procs 4. And you want to apply this function on each of the value of in the range 1 to 10. All you have to do is just do add distributed, I, 1, and 10. You call the function. What is that spawn? @spawn macro basically launches a remote function, a remote call to a function on each of the process. So this returns a reference to the result. So this is it. This is how you apply my function to 10 elements in an array, right? Extremely simple. So in conclusion, parallel programming empowers users to use this computational powers of multiple CPUs for faster and more efficient computations. So with its message passing interface, you have this like straightforward approach, which you can use for data parallelism, simulation, and so on, right? How can you use this in machine learning? That's a good question. So Julia's machine learning packages also use this distributed fact. And if you have a lot of custom architectures, there is even lower level of abstraction that you can use to simplify this parallelism. Distributed training is a huge use case of this, right? So if you distribute training across multiple machines and share the weights and so on, this is a much faster convergence, and you can handle much larger data sets, right? So there's another framework called Flux, which we'll cover in a bit, which provides like really efficient tools for distributed training. A model ensembling is also another use case, right? So you have multiple machine learning models which are trained independently, and their predictions need to be combined for accurate prediction. So you can ensemble the models using the straightforward approach. So if you have like ensemble learning, bagging, or boosting, where you have this parallel execution of model training, this significantly speeds up the process. So that's just how parallel computing in Julia enables like really efficient and scalable workflows. Some other reasons that I'm going to skim over is that Julia provides built-in support for GPU. So if you've heard of a package called CUDA, which is developed by NVIDIA, there is a support called CUDA.Julia. This allows us to use like CUDA features in Julia. And it also comes with the integrated package manager, which is really easy installation, management, and versioning, right? So if you have Python and you need to create environments, you have to do like VENV and so on, right? You don't have to do any of that. It's very simple, Julia. It comes with the inbuilt package manager. It also has a very rich development ecosystem, right? So there's a lot of packages like differential equations, plots, jump, Julia stats that are just focused on this numerical computation side. Julia is an open source language, which is a very key thing, right? So its community is known for inclusivity, friendliness, and willingness to help newcomers. So that's always a plus. But the biggest difference has always been that Julia was not like Python. It was designed specifically to address the needs of this HPC, where it combines like the expressiveness of dynamic languages like Python and the speed of statically typed languages like C++. So in my opinion, it lets you express some mathematical expressions as close to its true form as possible, which is really important because like this code readability and widely usage is based on that, right? So how fast can you develop? How low can you bring your development cycle? And that's what you need is this sort of language where you can really drill down on the development cycle, right? Especially in a time where it feels like we're lacking true innovation. I believe that this is a great tool. So there's also cross-platform, so you can run it on Windows, Mac OS, and other distributions. So let's move on to machine learning in Julia. So GPU programming in Julia enables users to leverage the power of GPUs. So you can accelerate these computations using GPU. So what you can do, let's look at the code example very quickly. So we first import the CUDA package and we define matrices A and B on the GPU. And we use this CUDA like random function. Then we perform some sort of like matrix multiplication using this multiple operator. You see this mul exclamation point. And what the exclamation point is basically, it's going to modify whatever container you pass to it. So you have a container of zeros labeled C, and you're saying that just put all the results into C. Right? There's also there's also a mutable one, which you just call mul A and B, but that returns a different matrix, which the compiler creates space for. So this is how simple it is to multiply matrices on the GPU, right? So Julia supports multiple GPUs, so you can actually harness like how many ever GPUs you have. And it also extends beyond, just NVIDIA GPUs. It supports, AMD GPUs. There's different packages for that, if that's the computing system that you have. And it relies on CUDA, right? The abstract low levels of CUDA are gone, right? So this just enables you to just focus on high-level syntax. Now let's take a look at another package, which is called Flux. Flux is a very remarkable package, right? So it's this package that offers several unique features that makes it stand out in the field of deep learning. Flux leverages dynamic nature of Julia to enable these neural networks or so on. So you can easily define and modify your neural network architectures on the fly. So here's an example of defining a fully connected layer. So you have this model equals chain. So chain basically combines all those layers. You're defining a dense layer of takes in an input of 784 and outputs 128. And the second layer takes in 128, outputs 10, and you apply this activation function on the layer. And so that's as simple it is to define a dynamic neural network. The other powerful tool is this autodiff, right? Automatic differentiation is a really cool thing in Julia because it's just really easy to do. So if you have your custom language, if you have your custom models, you're wondering how can I do autodiff on those? What you can do is there's actually other packages called chain rules that you can define your own derivatives and so on. So that just makes like backpropagation really easy. So in the example that I've given, there's a function f of x, and you compute the gradients using this gradient function, and that effortlessly finds the gradient for that function, right? So also GPU acceleration in Flux, so we can seamlessly integrate with the Julia's GPU capability. So you can see we've defined a model, and we just move it to GPU by just writing the straight line greater than. What's really cool is that this code executes even on CPU. So there's no need to write different code for GPU or CPU. If you can't find a GPU, it just runs on CPU. The last thing on Flux is there's this it's a flexible model selection, right? So you can load and save models really easily. So you have this user-friendly syntax. So you can build and train like state-of-the-art models, save and distribute them pretty easily. Listed some alternatives to Julia, in Julia to some of the packages that everyone most likely already uses. So data frames is a very versatile and efficient package for working with tabular data. Modeling Toolkit is a sophisticated package that lets you define and manipulate mathematical models, right? So if you have these complex math models in various fields, you can use that modeling toolkit. We covered plots, so I'm going to skip that. Differential equations is a comprehensive package for solving differential equations, right? So you have this wide range of solvers, and you can simulate, analyze these dynamic systems exist. So MLJ is this flexible Julia framework, which provides a unified interface for training, evaluating, and deploying machine learning models. So you can use this for production or commercial uses if you have the use case. We covered Flux. So lastly, we have Jump, which is a optimization package that provides like this high-level modeling language and solvers. So you can formulate and solve new optimization problems really efficiently. So if you're doing optimization work, Julia is also worthwhile. That brings us to the end of the theory. So let's jump into live coding now. So I'm going to stop sharing my screen and share a different window. Can someone confirm if you can see my screen?
That's visible.
Okay, great. So we're going to use this inbuilt package manager, and we're activating an environment that I created earlier. So it's very simple, right? And we're going to take a peek at the package.status, which gives you a summary of all the packages that you've installed. So this is actually it. You have this reproducible environment that you can distribute and people can take a look at. So let's see. So if you want to add packages, all you have to do is just package.add, some package. So if you want to add plots, which I've already added, so let's just run this. this should simply just update my plots package, if anything. So I'm going to use some other packages that I have not covered. So statistics is a package that just helps you compute, the mean, variance, and so on. And we have flux, which we covered. We're going to use the optimization thing from that. So, and we're using dates, and these are all some inbuilt packages in Julia. So GR is something that we not cover. So GR is basically the backend that Plots is going to use. So this is something that works on a MacBook, so I've chosen that. And there is some timeout error. I think it's an issue with my network. That's part of live coding. We have issues all the time. Okay, somehow worked. All right, so we're using all these packages. So what we're going to do is we're going to train a neural network that's just going to take some sort of timestamp, and it's going to output the epoch time, right? Which is basically the number of seconds that elapsed from 1970, January 1st. So this was chosen as the start time for all computers arbitrarily by the set of Unix engineers earlier in the day. So if you give it any timestamp, right? And if you in a timestamp, what you have is you have a year, month, day, hour, minute, and second, right? So you have 6 inputs, and you can imagine how this is a linear combination. Linear combination of these could give you the number of seconds that elapsed from that time. So this is something that you can approximate with the neural network. So what we're going to do is we're just going to set the seed in case you guys want to recreate this example. And we're going to generate some timestamps, right, from 2010 to 2020, and we're going to evaluate up to 2030. So what this does is we're basically generating a random set of vector from starting from first train to last train, which is 2010 to 2020. We're going to generate 1,000 examples. So we need to normalize our y. So we're defining a function because our output could range a very large number, right? So we're rescaling and we have a normalizer. So these functions, if you understand the high level, I think that's pretty sufficient. So we're taking our predictions, right, and we're bringing them back to the right scale so we can compute the loss correctly. That's what's happening in the rescaler. So for date time to input, what you have is you have the date time that we computed from our first train epoch, and we're going to take that and we're going to convert it to input, which is going to be our x values, right? So you do that is you just extract the year, month, day, hour, minute, and second. So these 6 are going to be our features in our neural network, if anything. So we're taking a bat size is 10. What this partition function does in Julia is it basically takes input and it groups it in bat size. So we have our output that we generated, and we're using it to extract the year, month, day, hour, minute, and second. And now we have our inputs and we have our outputs here. So we're going to define a very simple layer, which is just a dense layer that takes in 6 inputs and outputs 1 feature. So this is hopefully our seconds, right? And we're going to define our loss function as the mean square error function, which takes in x value. It runs it through forward pass through the model, and it computes the loss using the mean square. So let's run these cells actually. Okay, run this, and run this. Right, so you can kind of see what y's look like. So it's a normalized y. So that's why it looks like this. We're gonna have to pass this through the rescaler before we compute the loss, right? So here we're going to run this as well. And our training script is very simple. We trained this 1,000 times. And we're going to pass loss. And remember what this exclamation point basically means. You can edit this mutable container, right? So you're passing in the parameters of the model, which is just going to be 6 weights and maybe a bias term. And you're going to pass in a optimizer, which we defined to use Atom here. So we're training this model based on the loss criteria, which we've defined over here. So every 10th epoch, we're just going to push our loss to this array that we've defined over here, which is an array of 64-bit floats. We're going to run this as well. And now it ran pretty quickly, as you might notice, because we only have 6 weights. We're just going to plot the training loss, right? As you can see, we're learning something here. We're approximating this function, which is a pretty reasonable thing. And we're testing it. Oh, sorry. We're just training it based on the examples that we generated over here. All right. So that is the end of my presentation. So I hope everyone sort of learned something by Julia, right? And like, it's a pretty cool little thing, so you should check it out. So I guess I'll open the floor to questions.
Sir, I request all the participants to turn on your video so that we can go with the photo session. Request all the participants to turn on the video. Participants, if you have any queries that is related to this, you can start asking. This will be the query session. Any queries related, you can start asking. This will be the query session. You can leave it in chat box or you can just unmute yourself.
அப்போ அதுல வந்து கம்ப்யூட்டர் ரிலேட்டட் வந்ததுன்னா இப்போ என்ன ஒரு ஆத்தரை செக் பண்ணாலும் தப்பு கிடையாது தப்பு கிடையாது தப்பு கிடையாது.
If you have any queries, you can just leave it in chat box. That will be answered. Hoping there is no queries, I'll move with a vote of thanks. As we are near to the conclusion of the third day of our insightful and rewarding research tools FDP, it gives me an immense pleasure and gratitude on behalf of the entire department. I want to express my deepest appreciation to all the individuals and group who made this event possible. First and foremost, I want to express my deepest gratitude to our beloved HOD, Mrs. T. Kalai Selvi ma'am, and all the dedicated department staffs. Your unwavering support and mentorship has been the backbone of this event. We are grateful to the time and effort of Richard Rex sir devoted to preparing and delivering the enlightening session. Your dedication to sharing knowledge and empowering others is truly commendable, sir, and we feel privileged to have had the opportunity to learn from you. And a special thanks goes to all the participants out there. We understand that your commitment to professional growth and development is what makes the event like this so meaningful and impactful. Your dedication to acquiring knowledge and skills will undoubtedly have a positive impact on your respective fields, community at large. On behalf of the entire department, I extend our heartfelt thanks to the management of Easwari Engineering College for your unyielding support and encouragement. In closing, I extend my heartfelt thanks to once again everyone involved in making this third session of Research Tools FDP a resounding success. Let us continue to foster a culture of learning and collaboration, and may the bonds forged to continue to strengthen in the days to come. Thank you all once again. Wishing you success and fulfillment in all your future. Have a great day, and please make sure that you fill your feedback form that has been posted in chat box.
Ma'am, I have a doubt to ask to Sir Richard, sir.
Please, sir.
Yeah, hello.
Richard, sir, good morning.
Morning.
First of all, I'm much obliged that you have given this wonderful class for us. Sir, I just want to know that what is the scope of Julia in NLP area, natural language processing?
So I guess it might be useful to talk about the most leading paradigm in natural language processing, which is large language models. Everyone's so excited about large language models. And if you've been keeping up with the field of that, there's these things called like LoRa and these new Microsoft research that's coming out. And all of those would be much faster in Julia. So when I read these things, it makes me wonder why this thing is actually not in Julia. So if you're working on that, I encourage you to keep working on it.
Okay. Yes, sir. Thank you.
Yeah, of course.
Thank you very much for the wonderful session. Very grateful to hear from you. Thank you so much for your time, valuable time.
Yeah.
Thank you. I hope we will share the feedback to you directly, what we have received from our audience today.
Okay, thank you. I didn't realize I was not in presenter mode. I wish someone told me a lot sooner. I know that people are looking at speaker notes as well.
You did well. You did well.
Right,
It was
sorry
a great
about that.
session, actually. Yeah.
Noted an issue, sir.
All right.
Thank you so much. Thank you. Thank you. Thank you.
Thank you.
Thank you so much. Thank you, participants, for joining with us. Thank you.
Thank you, ma'am.